Well, we just have a look at a couple of problems that are relevant to Chapter 1, Section 5, and there's just a couple of these, questions 21 through to 23. So, 21 is about triangular numbers. It says if you've got a triangular number has the form of half n plus 1, prove that if m is the sum of two triangular numbers, then 4m plus 1 is the sum of two squares. Just a nice little result. Basically, it just boils down to some simple algebra. So here is the solution of this one, question 21. So if m is the sum of two squares, then it's a half a plus 1 plus a half b plus 1, I should say, for some integers a and b. And multiplying by 4 and adding 1 and expanding that out gives me this expression. Just taken the brackets out and multiplied by 4 and added on 1. And you want to write this as the sum of two squares, which you just do by really inspection. You can need a 2a squared, so you need an a squared and an a squared. You need 2b squared, I need a b squared and a b squared. Now here we're going to get a 2ab term, so we need a minus in front there to cancel out with that one. Now we needed a 2a and a 2b, so I put a plus 1 in here. That'll give me my 2a and 2b. And then I need a plus, and I get 1 squared as 1. So just a little bit of algebra there to write that as the sum of two squares, and it tells you explicitly how to write it. Question 22 says, show that the number 21 is not the sum of two rational squares. It's obvious that 21 is not the sum of two squares because it contains 3 mod 4 primes, so it's not the sum of two squares. We want to show it's not the sum of two rational squares. And so again, we do this by contradiction. We're going to suppose that you can write it as the sum of two rational squares, and without loss of generality, we can insist the denominators are the same. These may not be relatively prime, but that doesn't matter. We can write this. You can assume they've got the same denominator, and then multiplying across gives me that. So we're now back in the integers again. Now 3 is a factor of 21, and this double line here means 3 divides 21, but 3 squared does not. And so that means that this number here has a prime factor, which is not a square, which is 3 mod 4. And so this number cannot be the sum of two squares, so we get a contradiction. So a contradiction. Finally, question 23 says, if we take p to be an odd prime, show that if p can be represented in the form p is a square plus twice a square, then p has to be a 1 or 3 mod 8 prime. Now, primes of various shapes, of course, have been studied well. So people have looked at the squares plus twice a square, square plus 3 times a square, and so on, square plus 5 times a square, and so on. In this particular case, if we've got a prime that's of this shape, then it must be a 1 or 3 mod 8 prime. And again, the proof's fairly easy. So we assume that p can be expressed as a square plus twice a square. And so reading this modulo p, we get x squared is minus 2y squared. Now I should really point out here that I'll just do this over the side, that if p divides y, then p squared divides 2y squared, and that would then imply that p divides x squared, which would imply p divides x, which would imply p squared divides x squared plus 2y squared, which would imply p squared divides p, and that's impossible. So just a little side calculation here. So p doesn't divide y is what I want to say here, because I want to be able to say that y has an inverse. So if p divides y, then p squared divides this term, and then p divides this, p divides that, p divides x squared. Because p is a prime, if p divides a square, it divides the x. In that case, p squared divides x squared plus 2y squared, and then p squared divides p, which is impossible. So we know that y has an inverse, so you can multiply both sides by y inverse squared, and write then what you get over here as a perfect square is congruent to minus 2 mod p, and that says minus 2, the Legendre symbol minus 2 over p is 1, because minus 2 is now a square, and we know from question 19b that means p must be a 1 or 3 mod 8 prime. In fact, this is if and only if. And that's the solution to question 23.